Hello students. So in the last class we have studied about Liouville's theorem. Which says that the rate of change of the density function theory, the density function is equal to del rho by del t plus and we also learned about the postulate of equal a priori possibilities, where for some particular value of h, each point of the phase space is compliant and is with each value and is most equally likely to occur. Now, to further add to it, any choice of rho, any choice of the density function, any particular density function is actually the ensemble that we have discussed earlier. And a large collection of independent systems, all having the same values of their parameters EVN, are now this ensemble will have, as I have told you, is a large collection of the microstates. Microstates which are characterized by E, V, N mainly, and etc. And this is the first thing. And the density function also gives the probability that we find the system in a state. So it gives the probability that we find a system in a state Q P, and we can use this to find the value of average value, what is called an ensemble average. And this result is also called the fundamental postulate of statistical mechanics. lastly, the phase space volume which is accessible to the system, accessible to the system is actually proportional to the number of microstates. Okay. Now coming to statistical mechanics, we have three different types of statistics in statistical mechanics. One of them is your Maxwell-Boltzmann statistics. Another one is your Bose-Einstein statistics. And the last one is called the Fermi-Dirac statistics. These two are called quantum statistics, whereas this Maxwell-Boltzmann is called the classical statistics. Gases are basically follow MV systems, which are in the classical world, whereas subatomic particles like electrons, photons, they actually follow B or FD systems. Now, let us first start with the limitations of MV statistics. So, limitations of MV statistics. The first limitation is it is applicable to an isolated gas. So it is applicable only to an isolated gas, or by gas means isolated molecular system. And second limitation is that the potential energy, and there is no we don't consider mutual interaction, so that's why the potential energy is almost negligible, almost due to the mutual interaction between the molecules. And compared to the mean kinetic energy, gas is so this is negligible compared to mean their kinetic energy. This is one limitation, and other limitations are the gas is basically a dilute system, and there is a number of molecules. Per unit volume is small. Molecules PUV per unit volume is very small, and not only this, so this dilute makes it small also. The average distance or the average separation between the molecule is large. Average separation between molecules is large. Also, as we have discussed in the mixing of the gases, these Maxwell-Boltzmann, it doesn't lead to the correct entropy expression, and so we have a Gibbs paradox. It says that the entropy, there won't be any entropy change if similar molecules are present. So at T is equal to 0, this entropy becomes negative, and but this is actually not according to the third law of thermodynamics, which says that as temperature goes to 0, the entropy should also approach 0. This is one of the limitations, and this MB distribution, it actually cannot be applied to electron gas. So let us discuss how. So if an MB system, we usually use an FD system for electron gas, but let us see why it is not applicable for electron gas, because had it been used for electron gas, what are the limitations that would have happened? So a free electron should make a contribution 3R/2 to the heat capacity. So a free electron makes a contribution 3/2 R to the heat capacity. But the question is that this, so according to that they should share. So it implies that the electrons, these electrons, they will not share their energy to a conductor. So all the energy of the electrons are not given to the conductor. This is the first limitation, and the second limitation is the velocity distribution of photoelectron electrons produced by photoelectric effects. They actually are not agree with experimental results. Now, like from theory, if we go in theory, so this velocity distribution or the emission current density, go to emission current density. This J is equal to A t to the power 1 by 2 exponential minus phi by kT. Phi is the potential, and this is the theory, whereas experimentally you can observe that J is equal to A t square exponential minus phi by kT. So here it is to the power half, or here it is t square. So there is a discrepancy here. This is why this MB distribution cannot be used for electron gas. Now, similar to this, we will also see why it cannot be used in case of photons. So had it had MV distribution being used in the case of photons or photon gas. What limitations are there? First one is this emission predicts a continuously increasing number of photons per unit range of frequency as frequency increases. But actual distribution given by Planck's law, which is maximum falling off asymptotically on other side. So if we plot so according to MB, as the frequency increases, the number of photons should also increase. But this doesn't happen actually. According to Planck's law, although there might be a certain rise in the number of photons, so this actually it rises, but it falls asymptotically after that with a change in frequency on the other side. So this is the first limitation. Secondly, okay, so this is the limitations observed. So that is why electrons and photons, they follow different statistics. The electron gas, it follows Fermi-Dirac statistics, FD, and the characteristics of these are these particles have got half angular momentum or half integral spins, as you can say. We call it as n by 2 h cross, and they are called fermions since they follow Fermi-Dirac statistics, and they obey Pauli's exclusion principle, PEP, as well as Heisenberg's uncertainty principle. And examples of other fermions are nucleons, that is neutrons and protons. Then you have got helium-3, then mu meson. All these have got spin half. Bosons, on the other hand, are particles which follow Bose-Einstein statistics, but BE statistics. These are called bosons. And they have spin angular momenta, integral spin angular momenta, that means either 0, h cross, 2 h cross, 3 h cross, so on and so forth. So we'll call it as n h cross. And they obey Heisenberg's uncertainty principle, but not Pauli's exclusion principle. That is, means for one energy state you can have large number of protons and large number of phonons. And the examples of bosons apart from photons are phonons, the quanta of lattice vibration, then you have deuteron, pi meson, you have alpha particles, that means helium-4 nucleus. All these are the bosons. So deuterons have a spin s is equal to 1, whereas this alpha particle has spin s is equal to 0. So both of them can be considered as bosons.